Our speaker today is Vijay Natarajan, sorry, and he will talk about scalable computation of the Extremum Graph. Take it away.
Thanks, Teresa. So I'm Vijay Natarajan. I work at the Indian Institute of Science. I'm currently visiting the SUSE Institute in Berlin on my sabbatical. So today's topic is the Extremum Graph. And I would like to talk about computing the Extremum Graph. But prior to that, I would like to kind of introduce to you a particular application of this Extremum Graph, just by way of helping us understand the need for efficient computation and for scalable computation. So let me take you through this application to materials, especially granular materials. We are interested in the problems of segmentation and fabric quantification. So granular materials are materials like sand, seal, beads, coffee, or powder. Very interesting class of materials which have properties of both solids and fluids. This makes them very complex to study. They exhibit a lot of properties, very interesting properties. And they are of interest both from the scientific perspective and from an engineering perspective. Civil engineers deal with granular materials all the time. And it's important to understand them in order to build better buildings or bridges. So, but when I say segmentation, what I mean is the extraction of individual particles that constitute the packing within a granular ensemble. And when I say a contact network, what I mean is the geometric graph that represents the connections between individual segments or individual particles in this granular ensemble. So together with our granular mechanics partners, we are interested in the study of the fabric and its quantification. Actually, they are interested in quantifying the fabric, which essentially means understanding and quantifying the relative arrangement of particles within the ensemble, from simple statistics like coordination number, packing fraction, and so on, to more sophisticated measures, tensors and tensor field representations of the different contacts. Crucial to this as a first step is the segmentation of the individual particles and computing this contact network. From a computational viewpoint, the requirements are topological correctness, topological stability, in the sense that we would need the contact network to be stable across different particle sizes that could be present in the ensemble, and the data may be noisy. The method that we have also needs to be robust to the choice of parameter values. Ideally, we would like the method to be parameter free, but that's the holy grail, a bit difficult to achieve. We would like the method to be generalizable, so robust across different shapes of materials and different materials types. Naturally, we would like the method to be computationally efficient. We would also want the method for segmentation and contact network computation to scale to large data sizes, while still being able to compute these segmentations and the contact networks on a workstation. So typically, data analysis tasks do not have enough budget in terms of money to buy time in a cluster, typically. So we would ideally like to do these computations on a workstation. So towards this, we developed a pipeline for segmenting and analyzing CT scans of these granular materials. So this pipeline, I'm going to quickly go over this. It begins by considering a CT scan and considering it as a scalar field, computing a boundary surface that essentially is an envelope of all the particles within this ensemble. So this boundary surface is computed using a method that's parameter free, essentially, which it begins by computing an initial boundary surface that uses the popular Otsu's method, essentially a thresholding based approach, followed by an iterative refinement of the surface using a technique again from image processing called active contours. So this boundary surface is used to compute a distance field, which you see here on the figure. And the distance field is the input to our most theoretic based pipeline for segmentation. So we begin in this in the set of figures with the distance field that's extracted from one such granular ensemble. In this case, it's a synthetic example just for illustration. We begin by computing the critical points of this scalar field. And what I show here are only the maxima, the local maxima. I do not show the other critical points. Each, if you in 2D, if you think of each maximum as the peak, then we can associate the mountain corresponding to that peak. So similarly, we associate a region corresponding to each local maximum in this 3D volume. And this gives us a decomposition of the domain into these different segments. And so these segments are actually defined by so-called gradient lines or integral lines. The integral lines are these maximal lines that follow the gradient of the scalar field. And one can associate a collection of gradient lines that terminate at a given maximum. And this defines the segment corresponding to that particular maximum. So here the integral or the gradient lines are shown for two different maxima, 1 and 2, and colored by the scalar values, essentially the distance values in this case. One can quickly see that this collection of gradient lines provides a nice initial segmentation of the entire volume into these regions, one corresponding to each maximum. The interface, boundary interface between two segments contains the saddle criticalities, specifically the two saddles, index 2 saddles. The Morse complex is the topological descriptor that captures these segments together with the adjacencies between the segments. So each segment can be considered as a 3-cell, and this features in the Morse complex. The adjacencies between two different 3 cells is captured by arcs, which appears as arcs in the Morse complex. So if I compute the Morse complex, more specifically the Morse-Smale complex, I'm not going to talk about the difference between the two in this talk. The arcs of the Morse-Smale complex or the Morse complex, in this case, we care only about the arcs from the Morse complex that lie between the extrema or the maxima here and the saddles. They capture the adjacencies between the segments, and that provides us the contact network. So this is essentially the starting point for computing a useful segmentation. So just to summarize, we use the Morse complex of the distance field to provide to extract the segments as the descending three manifolds. These are the three-dimensional cells that I talked about, and the ascending one manifolds correspond to the arcs. The term descending and ascending refer to the fact that as you go from the critical point outwards, the function values decrease, so hence descending. And as you ascend in terms of function values from the saddles, you extract the arcs, and hence ascending. So this provides us the initial segmentation and the contact network. Of course, noise needs to be handled, and we do this via a principled simplification that is driven by the persistence of the different critical point pairs. Now, the persistence diagram and the persistence curve, which is essentially just the histogram of the number of critical points. I will show pictures later. So the persistence diagram and the persistence curve, essentially the histogram of the number of critical points against increasing values of persistence, provides a good a visual presentation that allows the user to explore the data and to identify an appropriate threshold for removing noise. And noise removal essentially is implemented as removal of pairs of critical points, so extrema saddle pairs. And removing each such pair corresponds to a merging of two adjacent segments into one. So this simplification allows us to prune the connectivity network. It allows us to remove spurious contacts between adjacent segments, and also merge particles that could be over-segmented. And hence allows us to kind of quickly converge to a connectivity network and a segmentation that is stable. Now, so we perform different results to kind of demonstrate the practical utility of this pipeline. The beginning with a calibration study on steel beads, which are just color-coded here to look like candy. But each of these is a steel bead of more or less uniformly the same radius. And the beads on the top are kind of chopped off because of the way the data is, a slice of the data is considered here. And on the right, what you see is the connectivity, the network. So more crucial is the application of this approach to arbitrary grain sizes and different shapes of particles. So we applied this to a cemented sandpacking ensemble, and each step in the pipeline contributes towards the quality of the results. So beginning with the active contour-based approach, which provides a better starting point as compared to the typical starting points used in related efforts, which is just based on a histogram-based thresholding and so on. So the active contours gives a good starting point, followed by the segmentation. Like I said, the persistence diagram and the persistence curve, the histogram allows us to identify a threshold for removing noise. And this allows us to extract good quality segments from this cemented sand granular ensemble. So we performed comparisons against the popular watershed-based approach. The watershed approach is essentially also a long pipeline. and requires a lot of post-processing. We do employ some post-processing with different parameters. So what we saw typically is that a principled kind of approach to removing noise allows us to to uh, avoid both over-segmentation, as you see here. Watershed results in over-segmentation, or it also could lead to under-segmentation in a few cases, and we are able to avoid that. Both these results are obtained using the same threshold for the most complex-based approach, as compared to different thresholds for watershed, to just to showcase the power of this approach. So this was extended later, more recently, towards extracting and analyzing such data after the segmentation and the contact networks are computed. The underlying algorithm for computing the most complex is based on a fast scalable algorithm that runs on the GPU and on multi-core CPUs. So this was developed earlier in our group, and an implementation of this algorithm called PyMS3D was used to as the core for this most theoretic-based pipeline. We extended the computation to support various visual exploration capabilities for extracting surface representations of these particles, for studying individual particles, their neighbors, for performing different statistics, for essentially quantifying the fabric. And all this is made available in a package called Morse-Graph, which is now, I think, available in the public domain. We are closely working with our granular mechanics collaborators to extend this and incorporate several of the algorithms that we have been developing over the past few years. So, but I want to highlight, in order to take me towards the next part of the talk, I want to highlight that the core of this this pipeline is the algorithm for computing the most complex and essentially the Morse-Smale complex. And we need fast scalable algorithms for computing this complex. As an aside, this motivated us to further improve the runtimes of the Morse complex. So I'm not going to talk about that, but there is another GPU-based implementation of the Morse-Smale complex computation, which is faster than PyMS3D by a factor of 7. It essentially, so for those of you who know about the Morse-Smale complex computation, it's essentially a sequence of graph traversal operations, which are known to be hard to parallelize. In the case of the Morse complex computation, we show how this how this graph traversal can be transformed into vector operations and matrix multiplication operations, so that they can, so that one can use existing fast matrix multiplication routines on the GPU to accelerate the computation. What I do want to talk about is specific to this particular application. What we required is the computation of this subcomplex, which included as nodes the maxima and the saddles that connected the maxima. Alternatively, this could be the minima and the one saddles. And the arcs were the one cells that connected the extrema together with the saddles. So this subcomplex, essentially a graph, is called the Extremum Graph. And we are interested in this Extremum Graph. Actually, we are interested in the Extremum, an annotated version of this Extremum Graph, namely one where the nodes are annotated with actually the function value at that particular node. In addition, the nodes are also annotated with the segment, the volumetric segment that they represent. The arcs need to be annotated together with different geometric characteristics, such as the interface boundary and possibly the area of contact and so on. So it's this annotated graph that we would like to compute efficiently rather than the entire Morse complex or the Morse-Smale complex. So towards that, we would like fast algorithms. The Extremum graph as a data structure has been studied in the past 10 years. It was introduced initially as a topological descriptor by Korea others. And they introduced this with the motivation of visualizing high dimensional data, and they provided an interesting visual representation of the Extremum graph in 2D. And that allowed them to visualize high dimensional data by via visual exploration of this 2D representation. Following this, there have been several applications of the Extremum graph. For example, to detect symmetry in scalar fields, both in time-varying scalar fields, essentially tracking features in time-varying fields. For comparing different fields by designing a distance measure between Extremum graphs. And more recently, towards the study of the efficacy of neural networks by understanding how the model behaves against different data sets. So I, of course, have not talked about the different applications of the Extremum graph that naturally arise because it's a subcomplex of the Morse-Smale complex. So these are just a sample of applications of the Extremum graph in itself. So motivated by this need to compute the Extremum graph, we worked on the development of an algorithm and an associated software library for computing the Extremum graph. So let me take you through that algorithm and the library. So this library called Tachyon essentially computes the Extremum graph in 2 steps. The first step essentially locates all the critical points and classifies them. This is pretty much a standard step in the computation of various topological descriptors. But there are some nuances here that allows us to kind of increase or improve the runtime efficiency. I'll talk about that. So critical point classification essentially requires us to process the neighborhood of every vertex, and we process these neighborhoods in a manner that is amenable to parallel computation on the GPU. After locating all the critical points, we would like to trace gradient paths from the saddles towards the maxima along the steepest ascent directions. So these are essentially path traversals, and we would like to perform this computation on the CPU again with acceleration using the multi-core architectures that may be available. So let's talk about critical point classification. Our method, just like various other methods defined earlier for computing topological descriptors, is based on this idea that the Morse index can be characterized by the Betti numbers of the lower link. So if I consider a particular vertex here, and if I look at if this is a maximum, and if I look at the neighboring vertices, the vertices that are adjacent to this particular vertex via edges in the input triangulation, then characterizing those vertices that are lower than the current vertex helps me classify this particular vertex as a regular or a critical vertex. Specifically, what we are interested in is the link of this particular vertex, and the link is essentially the boundary of the set of cofaces of the particular vertex that do not intersect with the vertex. So we can quickly see that the link of a vertex in a triangulation of the unit cube, let's say, would be a two-sphere. What we are interested in is the lower link, so the collection of vertices and the induced simplices, where the function value is lower than that of the vertex. So this is shown in green here. The lower link would essentially be the entire link in the case of a maximum. In the case of a minimum, the lower link is empty, and the upper link shown in red here would essentially be topologically equivalent to a two-sphere. So what we can quickly see is that the Betti zero of the lower link and the upper link provides an equivalent characterization, and this is what we use to locate the critical points and to further classify them. So this is essentially computable quickly on the GPU. It may seem embarrassingly parallel because every vertex can be processed independently by assigning a logical thread to each vertex on the GPU. However, there are several other GPU optimizations that need to be taken care of in order to ensure that this computation scales with the number of vertices. For example, for every vertex, we would like to, like I said, we would like to compute the Betti zero of the lower link. So essentially connected components of the lower link and connected components of the upper link. So for example, what you see here for a regular vertex is that the lower link has one component and the upper link has one component. In the case of a saddle, the lower link has two components and the upper link has a single component. It also has non-trivial one homology, which we don't need to explicitly compute since we compute the number of components of both the upper and lower links. So computing the connected components is a simple task. One would typically run a BFS traversal to compute the number of connected components. But as we can see that the size of the lower link differs significantly between the different types of vertices. And this leads to an issue with respect to synchronization when we want to run this in parallel. So what works better is if there is a similar amount of work on all the threads, and a union find a data structure based algorithm for identifying connected components scales better. And this is what is implemented in our library. So together with this, we also do not compute the link of each vertex explicitly. Instead, a simple case table allows us to look up the link and quickly classify its vertices as belonging to the lower or upper link and compute this the number of connected components efficiently. So these ideas lead to a scalable implementation of the critical point classification step. So next, we compute the gradient paths beginning from all the critical points. So for example, here we have a two saddle. So the two saddle is has two components of upper link, which are shown in red here, and the lower link has a single component. Gradient paths are originate from each component of the upper link. So there's one that begins from here and another that begins from here. And these paths are traced till they terminate at a local maximum. Alternatively, if minima and saddles are relevant in the particular data, then instead of tracing steepest ascent, we would trace the edges of steepest descent from the one saddles. So we terminate these traversals when the local maximum corresponding the local minima are reached. Again, each such traversal can be assigned to a different thread and can be run on the CPU using a simple parallel computation. Now, in addition, each gradient line can also be computed in parallel via a technique called pointer jumping. This works if the number of gradient lines is large in number. So we have implementations that attempt to do this as well. Right? In practice, we don't see much of a benefit in parallelizing each gradient line computation. So we employ parallelism across the different gradient line traversals. We would like the entire computation to run on this GPU and the CPU, even if the entire data set does not fit in memory. So towards that, we partition the data into blocks. And interestingly, we partition the data by slicing it along one dimension. So if, for example, if this is the data set, then we would just partition it into, let's say, 3 blocks along, let's call this the X direction. So that gives blocks 1, 2, and 3. The size of these blocks is computed by from a linear regression model, so which essentially gets data from a set of experiments run on a large number of data sets executed on different architectures with different number of cores in order to identify what size works best for a particular given GPU CPU combination. So in this case, CPU, since we are talking only about the gradient line computation as of now. So the gradient paths could tracing works as before. The only difference being that we restrict the gradient path computation to the particular block that we study. Now, if a particular gradient path attempts to cross the boundary, then we just pause the trace and resume the tracing when the next block is loaded into memory. So essentially, at the end of processing all the blocks, we have the Extremum Graph for our data set. In addition, we employ both the GPU and CPU to work simultaneously. So the critical point computation is required in order to do the gradient path traversal. However, while the GPU is busy trying to classify the critical points, the CPU lies idle. In order to engage the CPU simultaneously, what we do is as soon as a particular block is processed and the critical points are already identified, we send that data to the CPU, and so that it can begin the processing on that block. So this hybrid CPU GPU computation also reduces the runtime further. So we get good runtimes for large data sizes. So I begin by talking about the internal memory computation. So for data sizes, I begin with data sizes which are already 512 cubed and going up to 1024 cube. All these fit in memory. That's about 1 billion vertices. And the number of critical points here is about on the order of 20 to 80 million critical points in all these data sets. These are all 3-dimensional scalar fields. And the computation time, as you can see, goes from about 10 seconds or so up to 40 seconds. As compared to the previous approaches using the Morse-Smale complex, where the runtime, even for this, the smallest of this data set, the magnetic reconnection, was about a few hundreds of seconds. Data sizes which are smaller than this, smaller than the 512 cube, run within a couple of seconds. So I don't even show them here. What we see here is that the runtime naturally increases with the size of the data, and it also increases with the number of critical points. The critical point computation scales linearly with the data size, as we will see in the next slides. Moving on to data that do not fit in memory. So these are a few data sets which contain about 8 billion 8 billion vertices and up to about 2 billion critical points in some of them, in these two, actually. The runtimes are still manageable, a few hundred seconds, going up to the largest being for this 3D neurons, which has about 2 billion critical points. So the increase in the runtime, as you can see in this stacked bar chart, is primarily due to the gradient path tracing step, and which is understandable because as the number of critical points increase, we need to spend more time on tracing these gradient paths, and the partial termination of these paths also leads to a slowdown in the computation. The size of the data that can be handled by Tachyon is essentially limited by the CPU memory and not by the GPU memory. So this is still a limitation because we store the resultant extremum graph in memory, and that essentially limits the size of the data that we can handle. The method scales well with size of data, as you can see here. So this is a data set which is called the 3D Schweffel function, which can be sampled at different resolutions while kind of preserving the number of critical points. And what we see is that with increasing data size, the point classification scales linearly, and so does the total time for computation. We also see good scaling with the number of cores on the GPU for the critical point computation. So going from 768 up to kind of 8,000 cores on the GPU, the runtime does seem to reduce at a good along a good slope. So that's encouraging. The implementation also works on high dimensional data. So this Schweffel function is something that we computed or sampled in high dimensions as well, and tested the algorithm up to, I think, a few tens of dimensions, and it scales well even for high dimensional data. So in summary, what I would like to say is that the Extremum graph is a useful topological descriptor. I tried to motivate that via an application to the study of granular materials, particularly to segmentation of X-ray CT scans. There are several other applications of the Extremum graph to feature tracking and to high dimensional data visualization. What is the challenge is the computation of the Extremum graph, and the earlier approaches of where essentially employed this approach of extracting the graph from the MS complex. This became increasingly inefficient for higher dimensions. And we hope that Tachyon is able to address this, this need for efficient computation of the Extremum graph. It is able to support computation of data which do not fit in memory. It also scales or generalizes to higher dimensions. The library also provides utilities for simplifying the resulting extremum graph. This is still in the preliminary stages. While the simplification does work, it is correct. But in terms of computational efficiency, I think there is a lot that can be done here. So with that, I end, and I thank all the folks who did a lot of the work. So the work on the extremum graph and the granular materials was the master's projects of Abhijat and Dinesh, together with project staff who led the efforts on the granular material segmentation, Karan and Varshini. Our collaboration partners from civil engineering who are experts on granular mechanics, Tejas and Saurabh. We continue to work with them on improving and developing new techniques for understanding granular materials. We have part of this work is part of a larger project, an Indo-Swedish project with Linköping. So Tala and Ingrid are experts in visualization. So we work with them towards the development of useful visual analysis tools for materials applications and other applications. And of course, I would like to thank all the funding agencies for supporting this work. Thank you for your attention, and happy to take questions.
Thank you very much. Let's please all unmute ourselves so that we can clap together. Very good. Does anyone have questions? Okay, maybe I will start with one to get us warm. So somehow this talk reminded me of some work by Hubert Wagner about he programmed the software Cubicle, which computes persistent homology for image data. And it somehow seems a bit similar in spirit, because he also has those discrete Morse theory paths of collapses. But I think he's not so much interested in the discrete Morse theory complex itself, or these paths, but more in order to reduce the data size to then compute persistent homology. But I was wondering if you somehow know about that work and if you can somehow compare it, or I don't know.
Yeah, I'm aware of an early version of that, but I don't know the runtimes of the published work. I think I've heard one of his early talks about this cubics, I think, right? So I think before I start, so a key difference is that we are interested in the persistent pairs, but we are also interested in the geometric information that comes from the cells, or the one-dimensional cells of the Morse complex. In many applications, we are interested in the 2 cells and the 3 cells as well, right? But for example, with the extremum graph, we are interested in the segmentation and the contact network, so the arcs from the complex. So so this information requires us to do the tracing, and there is much that we can do by just computing the persistence diagram. But for this particular, there are many applications where we do need that geometric information. So that is, I think, the crucial kind of the distinguishing factor between the 2 approaches. But yes, what you kind of rightly summarized, I think the use of geometry for improving the runtimes of persistent homology is a different line of work, and we are not really competing with them.
Yeah, thank you.
Different goals.
I had a question. So I posted a link in the chat, Bitbucket, Tachyon. Is that the link that you would refer, for example, interested students to?
Yeah, thank you. Yeah, thanks very much. I should have put that in the slide, but yes, that is exactly the, yeah.
And for somebody like like me, who's not the most advanced computer scientist, is this pretty, is this code, should I think of this as code that is difficult to install or not so difficult to install, or, probably myself or one of my students could help me get started?
You should be able to install. So this is one of the few codes where we've got a replicability stamp. So,
Oh, wow.
yeah. So in the area of visualization and graphics, we have this notion of a replicability stamp, where a reviewer goes through the code and just ensures that things can be installed. There could still be bugs, but yeah. So. Yeah, if you are not able to do that, just reach out and we'll try to help out. Yeah,
That's fantastic. Thank you.
Any other questions? Okay, maybe I would have one. You said at some point you had a slide of applications and you listed several different applications, and for some of them, like the granular materials, it's pretty clear, like you went also a bit into detail of what the application would be there.
yeah.
But you also said something about testing different like artificial intelligence model on evaluate them on data or so.
Right. So yeah, so this, I think there are a series of papers. I list only one, which comes with a tool called NDDAV. So the idea is the following. So let's assume you have some high dimensional data. Then one way to explore this high dimensional data is to project it into lower dimensions using one of the standard techniques. I mean, beginning from PCA to I don't know, TSNE or what have you, right? Whatever dimensionality reduction techniques. The Extremum Graph or Mapper, for example, would be great ways to present that higher dimensional data to understand the behavior of to understand the data. So in this case, I think so what the authors were interested in was understanding the local minima of their landscape and how quickly that was reached, if I recall the application. And they used the Extremum Graph because it captured the different local minima and how they are connected to each other in order to understand this entire landscape.
Right. So kind of in order to understand the landscape that they're minimizing
yes.
in their neural network or so.
Right. Yeah.
Sounds cool. Yeah. Thanks. Okay, then if we have no more questions, I will end the recording here. But first, let me thank you again for your very nice talk.
Thank you. Thank you for inviting me.